All right, everybody. So today we're going to be talking about gas stoichiometry. And so today we're going to talk about how volume can be used as a conversion factor within stoichiometry problems involving gases. So first off, we have to discuss the kinetic molecular theory, aka KMT. So basically, the kinetic molecular theory is a set of guidelines, rules that we assume all gases follow. And so what we know is that particles are small, they're constantly moving, that they basically take up no space, that the volume of a gas is mostly the space between the particles. And so all gases are going to have the same behavior. If volume, temperature, and pressure are the same. So if I have different gases, but they're being held under the same conditions, whether I have carbon dioxide gas or hydrogen gas or helium gas, if I have those gases stored at the same volume, same temperature, and same pressure, then the number of moles is the same. And so basically, what this means is we can look at the conditions of a gas and we can use it to calculate moles. And it doesn't matter the identity of the gas, they're all going to have the same conversion factor. And so 1 mole of any gas, it doesn't matter, is going to have a volume of 22.4 liters at STP. So as long as that gas is being held under standard temperature and pressure, which again is 0 degrees Celsius and 1 atm. As long as that gas is being held under those standard conditions, it doesn't matter the identity of the gas, 1 mole of any gas is going to have that volume under those conditions, right? And so that's going to be the conversion factor that we use when we're doing gas stoichiometry. So 1 mole is 22.4 liters. Now, we have to be very careful with this. And the reason we have to be very careful with this is that that is not going to be true if we change the temperature or pressure, right? If I increase the temperature, then that's going to increase the volume. That was Charles's law. If I increase the pressure, that's going to decrease the volume. That was Boyle's law. And so only under those standard conditions is a mole of gas going to be equal to 22.4 liters. But if the gas is at STP, then this conversion factor can be used. Okay. So that means we can modify that mole map a little bit. We know we start off with a known amount of one substance, and we are asked to find a wanted amount of another substance. Now, sometimes our known amount is in grams, sometimes it's in moles, sometimes it's in particles, and now it could be in liters, okay? Same thing over here. Our answer that we want could be grams, moles, particles, or now we could calculate a volume in liters. And we know that the mole ratio is the link between my known substance and my wanted substance. Okay, remember that if you're starting with grams or you want to end up with grams, since we're using a mole ratio in the middle to convert things, we have to convert grams to moles or moles to grams. So we would use molar mass in that case as the conversion factor. If you're given moles, you can skip straight to the mole ratio, which is the coefficients in the balanced chemical equation. And then if you want moles, you're done after the mole ratio. No further conversions are needed. If you have particles or want particles at the end, remember Avogadro's number is the way to link the number of particles to moles. So we can convert to moles from particles, we can convert moles to particles at the end. And so now we can use that 22.4 liters at STP. Make sure it's at STP. Okay, so you have a problem up here. 5 grams of C3H8 is burned in oxygen. What volume of carbon dioxide should be produced at STP? So right there, we have a clue that we're going to be able to use that 1 mole equals 22.4 liter conversion factor. Okay, so looking at this, I think I'm going to need a 3 here, a 4 here, and then that's going to give me, I believe, 5 O2s right there. So I'm double checking. I think we're good. Okay, so I have 5 grams. I'm going to start my stoichiometry problem like I always do. Take that given amount. It's not new stoichiometry, we're just using a new conversion factor. The steps are the same. Read the problem, make sure you have a balanced equation, start with what you're given, and then go from there. So if I need grams of C3H8 as a conversion factor, I have to use the periodic table. And so that's going to be 44.097 is 1 mole of C3H8. Okay, so drop that down. And if I look at my balanced chemical equation, for every 1 mole of C3H8, we produce 3 moles of carbon dioxide. But I want to know volume, aka liters of carbon dioxide. And so what I'm going to do is drop down my unit. Carbon dioxide is a gas. 1 mole of carbon dioxide is going to be equal to 22.4 liters because we're at STP. So I can just use that as a conversion factor within my dimensional analysis. So just so that we have an answer, I got this in my calculator. It looks like my given amount had 3 significant figures. So that would be 7.62 liters would be the answer, because liters is the unit that I'm left with. Okay, so then right here, what if the gas is not, and that's what that should say right there. What if the gas is not at standard temperature and pressure? Let's say that I have that 5 grams of C3H8 burning in oxygen, so I get to use the same equation up here. But what volume of carbon dioxide is going to be produced if my conditions are changed from STP to 500 degrees Celsius and 2 atmospheres? Okay, so here's the game plan whenever we have a problem, a stoichiometry problem, that is not at STP. So first off, do the stoichiometry. Through the mole ratio, right? That will calculate moles of wanted. So then you can take moles and use it in the most useful of gas law equations, the ideal gas law. So basically what we can do is we can do this problem up to here. We can take that 5 grams of C3H8 and work our dimensional analysis through the mole ratio and stop after the mole ratio. So if I do that, if I go ahead and do that math right there, that's 5 times 3, that's 15, divided by 44.097. So if I do this stoichiometry problem and stop after the mole ratio, what I end up with is 0.340 moles of carbon dioxide. Okay, so that's how many moles of carbon dioxide are going to be produced. That's going to be N in the ideal gas law. Then if I look through the problem, I have 500 degrees Celsius, which is equal to 773 Kelvin, and that's going to be the temperature that I drop into this equation. And then they gave me 2 ATM, no, it's actually 2.0 ATM, and that's going to be the pressure that I use in this ideal gas law. And so then we can plug all of those values into this ideal gas law, and we can solve for volume, because the question is what volume of CO2 should be produced. So we can use the ideal gas law in conjunction with stoichiometry. Remember that stoichiometry is all about moles, the mole ratio, and the ideal gas law has moles. And any value for pressure and temperature can be used with the ideal gas law. So if our gas is not at STP, then we can simply stop at moles and use the ideal gas law to solve for our wanted volume. So again, if I was going to solve this problem, my pressure is 2.00, volume is unknown. I have 0.340 moles. Since the pressure is in atmosphere, I'm going to use 0.0821 as my R value. And then the temperature, after I add 273 to convert it to Kelvin, was 773. So 0.340 times 0.0821 times 773. That gives me 21.6, pretty much, on this side of the equation, is equal to 2 times V. So I need to divide both sides by 2, and I end up with an answer of 10.8. And since this is the ideal gas law, that volume is always going to be in liters.